So in today's discussion, we will start discussing things regarding special relativity. We will touch upon the concepts of special relativity and we will see the manifestations of various invariants which special relativity comes up with. And then we will try to see in the coming lectures what happens when the concepts of special relativity is applied to quantum mechanics and what their marriage gives rise to the so-called relativistic quantum mechanics and quantum field theory as well. So let us get going. In this discussion, I am going to touch upon the basic ingredients of special relativity and the two central concepts which are very core to the discussion of relativity or special relativity is that when we talk about physics in inertial frames, two things should be very sacred to all inertial frames. One is that the speed of light that should remain same in all inertial frames. So that is one proposal special relativity comes up with. And the secondly, whatever we describe as a laws of physics should also remain something same in all inertial frame. That is to say, a technical word for that is they should be of invariant form in all inertial frames. So there are two different things which these two concepts give rise to. The first thing is constant. The speed of light remains same. That is the same constant value in all inertial frame. So the word constant will mean no change at all. That speed of light in one frame is whatever value is there. In other inertial frames, the same value is recovered. However, in the second concept, which is the laws of physics, we are using the word called invariant form. The invariant form tells us about that the parameters or the variables which are there in the laws of nature or laws of physics, which are expressed in terms of some equations, those variables or different parameters in the equations, they are allowed to change. However, the relation maintaining different variables should remain the same relation across different frames. So in that invariant form, we are saying that the structures of the equation should remain same, not their values. I'm not demanding that if f is equal to ma, f should remain the same and a should remain the same. Despite we are demanding that f should always be equal to ma, whatever value you find in the different inertial frames. Okay, so these are the two core concepts with which most of the discussions of special relativity relevant for our course of quantum theory would be useful, can be dealt with. So just to remind you about various things, the various subtle points which are different in special relativity when compared to Newtonian gravity, is that Newtonian gravity is essentially dictated by transformations which are known to be Galilean transformations. So different inertial frames where we are trying to write laws of physics are identified or related to each other through Galilean transformations in Newtonian relativity. What are Galilean transformations? Galilean transformation is that if you are an inertial frame and there is another inertial frame which is moving with respect to you, with respect to some velocity called v0, then the coordinates of your inertial frame and the other inertial frame which is moving with respect to you are related by these transformations. That your coordinates are x and t, the other inertial frame's coordinates will be x primed and t primed, and the Galilean transformation suggests that your coordinate and the different inertial frame's coordinates are related by a velocity times the time difference. Meaning, if another frame is moving away from you with some velocity v0, it would find that its location is given by this expression x minus v0 t. Okay. Similarly, for time in Galilean transformation, it is suggested that time would not change across two different inertial frames. So time will remain the same. So if we have one inertial frame which is s and another inertial frame which is moving with respect to s, so call it s primed, then suppose we are talking about a point x over here, so call it point P rather. The point P has a distance x in the frame S, while it has a distance x primed in the frame S primed. Now, as the frame S primed is moving towards the point, its distance gets shorter and shorter over time. So whatever was x, the distance of the origin from the projection of that point would get shorter and shorter. So that is how this x prime is equal to x minus v naught t is written. Okay. So let us say this between this s and s primed, which is having coordinate x primed, this is t and this is t primed. So this is moving with respect to the first inertial frame with velocity v naught. Now the time remains the same. The time flows in the same fashion across these two inertial frames, which is what Galilean transformation assumes. Under this, it so happens that the velocity of a particle as seen by frame S, suppose there is a particle here rather. I should not draw it on the temporal axis, but just on the spatial axis. So suppose there is a particle which is moving with certain velocity, call it some velocity which is v as seen by observer in the frame S. So that observer says that the particle what we are seeing is moving with respect to it with a velocity v. So dx upon dt is v. Now the same particle will appear moving slightly slower when compared to an observer in S prime frame, because S prime frame itself is moving with velocity v naught. So from these transformation laws, you can find out what is the velocity as seen by the observer in S prime. So that would be dx primed upon dt prime, which is the velocity as seen by the observer in the S prime frame. And it so happens that x primed is x minus v naught TL, while t primed is just t. You can convert this equation into that. So you can see that the velocity as seen by observer in the second frame S prime is velocity as seen from the first frame dx upon dt minus v naught. So it is somewhat lower the velocity. So velocities do change under inertial transformations detected by this Galilean way. However, under this transformation, what remains preserved is the acceleration. So you can similarly compute what is the acceleration of the particle as seen by the two frames. So from the first frame, the acceleration will be d2x upon dt square, while in the second frame, it would be d2x primed upon dt primed square. Again, use the information that t primed is just t and x primed is x minus v naught t. You can see that under second derivative, the deviation term, this v naught t terms, is killed out. Under double derivative, it does not contribute. So therefore, the accelerations across two different inertial frames remain the same. So that's why the Newton's law, which was given as acceleration is equal to f by m, the second Newton's law, in an inertial frame, the acceleration generated by the action of any force is given in terms of its force divided by the inertial mass, remains the same across all inertial frames. So given a force, how much of acceleration will be generated is a frame independent answer in the Newtonian mechanics. So this was the setup under which Newton's laws operate. However, as we have seen from the second point itself, the velocities do change across different frames. So therefore, it is in direct conflict with the first assumption the special relativity tries to propose, that the speed of light should remain the same in all inertial frames. In order to accommodate this demand, people try to come up with another set of transformations which respects this demand that the speed of light remains the same across all inertial frames. And ultimately, we ended up landing on a set of transformations which are called Lorentz transformations, which are different from Galilean transformation in the sense that in this transformation, not only x and x primes change, and the changing relation is different compared to what it was in the Galilean transformation, the times also do not flow with the same rate as proposed in the Galilean transformations. Time also change across two different frames. So in one frame, if the particle's location is given by x, in the second frame it is not x minus vt as it was proposed in the Galilean transformation. It is x minus vt upon square root of 1 minus v square upon c square. Similarly, time is in the second coordinate is not equal to the previous time. T prime is not t, but it is t prime is equal to t minus some v upon c square times x. Actually, all the v's here should be v naughts. So t prime is equal to t minus v naught x upon c square divided by this strange function square root of 1 minus v naught square upon c square. So if you try to accommodate the demand of constancy of speed of light, actually one can work out that when the particle moves at the speed of light, when it so happens from this transformation, if dx upon dt happens to be c, you can prove from this relation that dx primed upon dt primed also happens to be the c. This is what is special about this transformation, that it protects c. This doesn't happen for any other number. If dx upon dt is not c, then its counterpart in s prime frame is not the same value. It will change. Only for the value c it works out. So therefore, these Lorentz transformations respect the first demand of special relativity, that speed of light should remain the same in all inertial frames. And therefore, in order to accommodate that, we are forced to adopt these transformations, which are different from Galilean transformations. One can see that whenever v naught upon c square or v naught upon c is a very small quantity, very ignorably small quantity, then these transformations become the Galilean transformation. So the strange looking functions in the Lorentz transformation have this property that v naught by c tending to 0 limit is the Galilean transformations. So therefore, if we are moving with a speed much smaller compared to the speed of light, I can work with Galilean transformations equally well, because this is the limiting case of Lorentz transformations. But as soon as I start dealing with particles which are moving with higher and higher velocities, then the transformations should not be used as a Galilean transformation, because they do not respect this demand that the speed of light should remain the same. This is a whole set of discussions why speed of light should remain the same in all inertial frames, which I encourage you to look on any special relativity literature, like Michelson-Morley experiments and whatnot. But given this premise that the speed of light is supposed to be same in all inertial frame, we are forced to use Lorentz transformations rather than Galilean transformations. In order to accommodate the demand of constancy of speed of light, we landed upon these transformations, and the cost we pay is this, that unlike the Galilean transformations where the accelerations was the same in all inertial frames, then it so happens that d2x upon dt square does not remain same in all inertial frames under Lorentz transformations. So therefore, if this was supposed to be law of nature, that the response of a particle on application of any force, then this response does not remain same across all inertial frames. Under Galilean transformation, it was true that the response which was generated, which is d2x upon dt square, had the same value across all inertial frames. So that was this, it was an acceptable law of physics. However, if I adopt Lorentz transformation, this statement is no more true, that accelerations do not remain same. Therefore, the Newton's law, which tells me that d2x upon dt square is the response of a force, does not remain same across all inertial frames. So therefore, this cannot be acceptable as a law of physics. The second law of Newton's mechanics is not the law to be applicable on particles which are moving with faster velocities, and do see the Lorentz transformation as a correct set of transformations across different inertial frames. Just to summarize the discussion, where do these functions, strangely looking functions, come up with? I assume you have seen it before as well, but I will just quickly wrap up the discussion with this small set of exercises from where one can see the demand of constancy of a speed of light. How does it uniquely give rise to the Lorentz transformation? This is set upon by the demand that if speed of light has to be same across all inertial frame, then the distance traveled in one inertial frame by the light, dx square plus dy square plus dz square, should be the same as c square dt. So c is the speed of light, the time elapsed is dt. So this is the time elapsed times the velocity squared should be the same as the distance traveled. And that statement should remain true in all frames. That is a demand, that I will use the same speed of light but with different time interval and different length intervals as well, but that ratio should remain the same. So this relation should remain true in all inertial frames, and this relation is telling me that the particle is traveling with speed of light c. So I'm not using c prime here, I'm using c, and that is the statement that the speed of light remains the same. They might have traveled for different distances in different inertial frames. They might have traveled for different temporal durations in different inertial frames, but the ratio of the distance traveled by the time elapsed remains same across all inertial frames. So that is what our demand is, that this quantity should remain same in all inertial frame. That's why we are looking for a transformation which keeps this invariance protected. How should we relate t and t primed, x and x primed, y and y primed, and z and z primed? So since in a simple case we can assume that particle is moving only along the x-axis, or two different inertial frames are just moving away from each other along one particular axis, call it x-axis, then nothing changes in y and z direction. So y prime should be y and z prime should be z. And I suppose that there should be a linear relation combining a linear relation relating the t primed and x primes to their counterparts in another inertial frame. So linear transformation, a of t plus b of x, e of x plus f of t. These a, b, e and f, they are supposed to be constants. I'm using symbols a, b, not c and d, because c I'm using for speed of light, and I'm not using d because dx, dy, dz, d appears at various places. Therefore, in order to not to confuse people, I'm using a, b, e and f. Now this a, b, e and f should be constants of time and space both. They cannot depend on time and they cannot depend on x. Otherwise, the relation will change from time to time. If it is a function of time, then that relation what we are proposing will change from time to time. Today, if this is this relation, tomorrow it will become some other relation. And if it is a function of x, it will become the relation will change from place to place. If here the relation is some quantity, some expression, then at some other places, let us say in other part of the earth, it will become some other relation. If I want the same physics to be operating at all places of inertial, all places of universe, let us say inertial universe, and at all time it should be protected, that means there is no special day. Today should not be a special day compared to tomorrow or day after. Then, and this point should not be special to some other point in space. Then a, b, e and f should be constants. They should not be functions of x and t. With this assumption that these are functions, these are not functions of x and t and constants, we try to see what kind of constants will protect this relation. So since we have assumed y prime is equal to y and z prime is equal to z, therefore dy prime will be equal to dy here, and dz prime would be equal to dz there. So therefore these two can be cancelled out on both sides. Now, in order for this relation to work out, left hand side remains like this. Right hand side, I'm going to write for t prime the first relation, and for x prime the second relation. Okay, so a dt plus b dx whole squared, because dt primed square is supposed to come here, and dx prime square is supposed to sit here. So dx prime would be e dx plus f dt from this expression, and then square it. Now you see from the square of the first quantity, something times dt square will be generated, something times dx square will be generated, and a cross term which is dt dx will be generated. And same thing will happen for the second term's square as well. Something times dx square will be generated, something times dt square will be generated, and a cross term twice of e times f times dx dt will be generated. So in the next step, what I do, I collect all the terms which are proportional to dt square. So all the terms which come with dt square is collected one place. All the terms which come with dx square is collected at another place, and all the terms which are cross multiplication between dt and dx is collected at one place. So I just opened it up. The coefficient of dt square will be c square times a square from the first term and minus f square from the second term. So dt square will come with the coefficient c square a square minus f square. Dx square will come with the coefficient c square times b square, c square times b square with a plus sign, which is minus and minus here. I have written in a funny way in order to compare it on the left hand side. And from the second term, the coefficient of dx square will be just e square with a minus sign. So this is fine. Now the last term, which is the cross term, which is getting generated. From the first term, I will get a term twice of c square times ab, which is here. And from the second term, I will get twice of e times f, which is here. So ultimately, the right hand side is a collection of something times dt square, something times dx square, and something times dt times dx. And that should better match the expression on the left hand side. So therefore, component wise, the coefficient of dt square should match the coefficient of dt square here. Coefficient of dx square should match the coefficient of dx square here. And coefficient of dt dx should vanish because left hand side there is no dt dx. So that gives rise to various identities across these constants, the four constants. C square a square minus f square, which is the coefficient of dt square on the right hand side, should match the coefficient on the left hand side, which is c square. E square minus b square times c square, which is the coefficient of the dx square, should match the coefficient of dx square on the left hand side, which is 1. And twice of abc square minus ef should be 0, which gives rise to identity abc square is ef. So these are the three identities, relations amongst the constants a, b, e, f are generated by demand of constancy of speed of light. Now there is plain simple algebra to follow. Since here I can see that a is nothing but ef upon bc square. A is ef divided by this bc square, and that a I can feed up here. So I will get this relation, e square times f square divided by this b square c4, which is coming from the ratio ef upon bc square, which was a. So this relation can be written like that. All right. Once I have written like that, you can see that c square is cancelling the c4 here, so that it will become 1 over c square. And then I can write this expression as, I can pull out f square upon b square c square here, and inside I will get e square minus b square c square. So this left hand side of this can be written neatly as this. Okay. Now use the second identity, that e square minus b square c square is 1. So you will see that e square minus b square is 1, and this side I have a c square already. So I would get a relation f square upon b square c square is c square. This is 1. Therefore f square will be b square c to the power 4, and therefore the square root will be f is equal to b c square. Okay, f should be bc square. All right, this is fine. Then I feed this information in the first equation again. First equation was c square a square minus f square. F square will become b square c to the power 4. Therefore, I can pull out a c square common to both the terms, and I will have this identity. which again c square will get cancelled, and I will have a simple relation a square minus b square c square is 1. A square minus b square c square is 1. And secondly, from here, since BC will be f upon c, from here f upon c is BC, I can write this e square minus BC whole square as e square minus f upon c whole square. So these two identities I have converted these identities here into these two identities, which are useful. This is plain and simple algebra, just mathematical jugglery we have done. Now let us apply the physical input that we want to look at. Again, as we discussed, there are two frames, S and S prime, and S prime frame is moving away from S with velocity v naught. So at time t, if this is my origin of S here, the origin of S prime will be at location x is equal to v naught t. So x should be the location of the origin of S prime. This would be v naught t according to observer in S. Alright. According to observer in S prime, the location of the origin will still be x prime is equal to 0. Because for this observer in this frame, the other frame is moving backwards. Its own frame is stationary as seen by this guy. So therefore, this guy will say that, oh, okay, my location is x prime is equal to 0. So therefore, after time t as seen from frame S, the location of the origin of the second frame is v naught t, and while the second observer says that location of the origin of its own frame is at x prime is equal to 0. So x prime is equal to 0 should be obtainable from the expression we just wrote down. X prime should be ex plus ft. So x prime is equal to 0 should be ex. Ex was v naught t. I am writing v naught t in a funny way, v naught divided by c and multiplying by c. So this is just v naught t plus f t. F was bc square. We had written f was bc square and x prime was ex plus ft. So I have a relation that 0 should be equal to e times v naught upon c times ct plus b times c square t. So you can see that c is common in various places. So you can use this relation and write down that e v naught upon c square is minus b. This expression, left hand side being 0, gives you e v naught upon c square is minus b, which is fine. And now we have everything set up. The second identity which we just wrote down here, now let us put that to business. E square minus f square upon c square is supposed to 1, which is here. Now we use the identities which we have just derived. E square I will leave like that. F was bc square, so its square will be b square c to the power 4 divided by c square coming from here. So this will be this relation, okay? And b itself is e times v naught upon c square. So use all of this information, and this information will nicely convert itself into e square minus e square times v naught square upon c square. And therefore e should be square root of 1 upon 1 minus v naught square upon c square. So the first parameter e, which appears over here, has been identified to be 1 upon square root of 1 minus v naught square c upon c square. The second parameter b can be obtained from this expression. Once I know e, what I have to just do, multiply a minus of v naught upon c square. That's what I do. So b is also obtained from this relation. Similarly, f can be obtained from the relation f is equal to bc square, and I will get just this f. And lastly, a is ef upon bc square, which was obtained from the last relation over here. So once I knew e, all other parameters can be fixed. So then I know what is a. A is just 1 upon square root of 1 minus v square upon c square. B is just minus V naught upon C square times this factor. E is just square root of this quantity again, and F is this minus V naught upon this thing. So therefore, I get a transformation which initially I wrote down as AT plus BX and then EX plus FT. This expression ultimately gives rise to the low-range transformation. So the low-range transformation which we wrote down earlier as a proposal is now derived as a result of the demand of constancy of speed of light. Okay, so you can just do the algebra once again at your convenience to settle this idea that all we have to use is to demand that speed of light remains the same across two inertial frames. That is, this quantity, the same C should appear on both sides, and after that you just demand that it's a linear transformation because of homogeneity and isotropy of space and time. And after that, the algebra is straightforward to lead you to the fixing of the coefficient A, B, E, and F, and you do land upon low-range transformations or given LT. Okay. So I stop here for this discussion session. In next discussion sessions, we will see what kind of new physics this low-range transformations gives rise to and what kind of new laws of physics we land upon. Okay, so I stop here.